Welcome to the GaN Talk podcast, brought to you by EPC and hosted by Maurizio Di Paolo Emilio, Marcom Director at EPC. This show brings to life the stories behind GaN technologies and products. In each episode, you'll hear engineers, executives, and academics share insights on the challenges and opportunities shaping the GaN market. Here is your host, Maurizio Di Paolo Emilio.
Hello everyone and welcome to GaN Talk podcast in this new episode. Today we are talking about the evolution of motor drive technology and how GaN power devices are enabling a new generation of compact, efficient and high performance systems. Our guest is Federico Unnia, Manager of Applications Engineering at EPC Efficient Power Conversion. EPC has just introduced the EPC91202 evaluation board, so a three-phase BLDC motor drive inverter capable of delivering 50 amp RMS phase current and switching frequencies up to 150 kilohertz based on 100 volt GaN FET. The design targets demanding applications such as robotics, drones, e-mobility, and so on. So today we will explore how GaN is reshaping motor drive architectures, what this new platform enables, and where the technology is headed next. Hi Federico, welcome aboard. How are you?
Hi Maurizio, thank you very much.
Good. So, as I mentioned at the beginning, motor drives are becoming increasingly important in applications such as robotics, drones, and so on, battery power systems as well. At the same time, designers are pushing for higher efficiency, smaller form factors, and so on. So, my first question to you, what are the key limitations of traditional silicon motor drive solutions, and how does GaN technology help overcome them?
That's an excellent question, and that's actually the first question that we had, and we have still today to answer when introducing GaN technology in motor drive applications, since they're typically using silicon parts. The main limitation of the silicon MOSFETs in general with respect to GaN transistors is that if they have the same on resistance, silicon MOSFETs have much bigger capacitances, which makes them much slower in switching. And that's a limitation in terms of the maximum switching frequency that they can be operated at, because if they go into higher frequency, they lost too much energy. And so the key limitation of the traditional silicon motor drives is the switching frequency. They cannot go above a certain switching frequency. And at the same time, and consequently, they cannot go below a certain dead time. And this is where GaN can really improve in terms of electrical characteristics. So the first thing is that the dead time can be shorter and the frequency can be increased.
Great, thank you. So EPC, as I mentioned, recently introduced the new board, EPC91202 evaluation board, so a complete three-phase BLDC inverter capable of delivering up to 70 ampere peak current and operating PWM frequencies up to, as I mentioned, 150 kilohertz. So can you describe this board? Can you walk us through the architecture of this board and the main design choices behind this platform?
Sure. So this board is meant as a very quick board to test directly in the lab GaN in motor drive applications. So it's a complete inverter. It has a connector for the controller boards, and this is compatible with all the main controllers manufacturers that make microcontrollers for motor drive, like ST Microelectronics, Microchip, Renesas, and Texas Instruments. So any controller that the customer is used to can be used with this board. It has connectors for the DC link, like the battery or a generic power supply, and it has all the remaining building blocks of an inverter. So the power stage per se, the DC-link capacitors, the current reading, which in this case is made with Hall sensor based current sensors. It contains the housekeeping power supplies, so there's no need to supply the 5 volt and the 3.3 volt for the microcontroller externally. It's already generated on board from the main DC connection. And of course, there are all the parts to correctly drive the transistors, so the gate drivers. And it also has some protections. The first and most important protection is the overcurrent detection circuit. So once the measured current that flows towards the motor exceeds a certain value, a fault signal is sent to the microcontroller, and the operation is immediately shut down to prevent the board from overcurrent damages that may break the device. And also, although they are not necessary, there are anti-parallel diodes, silicon diodes, in parallel to the GaN FETs, because it might happen that a firmware derived from older silicon application is used, and these firmwares usually have very long dead times, which are not suitable for GaN, but still we usually place these optional diodes to prevent damages due to a very long dead time that might be used incorrectly.
Okay, good. So one of the features of this inverter is its ability to operate at switching frequencies. What advantages would this feature would bring in terms of motor performance, torque, density, and system size?
So increasing the PWM frequency has benefits both on the inverter side and on the motor side. On the inverter side, the higher switching frequency allows to dramatically decrease the size of the input filters, like the DC-link capacitors, because the dimension of the DC-link capacitors depends on is inversely proportional to the switching frequency. So, like increasing the switching frequency, for instance, from 20 kilohertz to 100 kilohertz makes it possible to reduce by 5 times the dimension of the DC-link capacitors, which means a reduction in terms of volume, weight, and also cost. And this is the advantage on the inverter side, one of the advantages of the inverter side. While on the motor side, a higher PWM frequency results in a cleaner waveform, and the waveform of the motor phase current, which is closer to a pure sinusoid, which makes the excitation of the motor more similar to a pure harmonic excitation, which makes the motor typically less noisy and more efficient. And thanks to the reduction of the dead time, that has an impact on the harmonics that are sent to the motor, because if the dead time is very small, the modulation doesn't have a discontinuity that is present when the dead time is big, and in that case it eliminates the fifth and seventh harmonic on the current, which again results in less vibration and higher efficiency of the motor.
So the board integrates current sensing, voltage monitoring, temperature monitoring, and as you mentioned, protection circuitry. So how important is integrated sensing and monitoring for enabling advanced motor control techniques like field-oriented control, space vector, PWM, and so on?
Mm-hmm. So the first important thing is that there's no need for any extra equipment in using this board. It can be really plugged in the motor, the battery, and into the microcontroller, and once the firmware is flashed, the motor runs. And in particular, for what concerns the current sensing is measured in the phase. So the current is measured through all the PWM cycle, And that makes it possible to have a very high modulation while always reading the current. So it makes the current reading more accurate than other methods.
So one of the key challenges with wideband gap devices is managing switching speed and DVDT to avoid EMI issues and maintain stable system behavior. So from design perspective, what techniques are used in this platform to control switching transients while still maintaining the efficiency benefits of GaN devices?
Mm-hmm. So for what concerns discrete, but also integrated circuits, this is the case of discrete. The gate drivers have a split output. So the signal that drives the gate of the GaN transistor is not a single signal, but it's a split signal for turn on and turn off. This allows to use two different resistors to turn on and off the GaN. The turn off is it's important to shut down, so to turn off fast, very fast, the GaN part always, while the turn on is important to tune it to according to the application. In the case of motor drive applications, there's no need to turn on particularly fast. So because that results in a slower DVDT, slower compared to other GaN applications, but still faster than MOSFETs. But this results in a slightly slower slew rate on the switching node, which allows to keep EMI emissions and low and to reduce the source of electromagnetic noise. So the first and best way to reduce possible electromagnetic problems is to tune properly the on resistance. And the second one is, of course, to do a proper layout, because once the layout with the decoupling capacitors is performed correctly, then all the ringing and overshoots and every kind of aspect that brings to EMI interference is reduced on the board.
Good, very good. Thank you. So let's talk about thermal performance. So high current motor drives operating at this frequency, high switching frequencies would create demanding thermal conditions. So especially when we are talking about robots, drone platform where space is limited. So how do GaN devices impact thermal management and power density in motor drive systems? So what engineers are considering when designing high current GaN-based inverters?
That's an excellent question, because GaN has a very particular feature, which is the topside cooling. So while most of the SMD packages for silicon MOSFETs have allow only for bottom side cooling on the PCB, the GaN parts have an exposed eye. So top side cooling is very efficient. But at the same time, we've also observed that using proper layout techniques, it is also possible to improve concurrently the cooling from the PCB. And that is, in fact, let's say, put in practice by using heavy layers of coppers close to the device. So it's important to use the highest possible copper thickness in the layer where the devices are assembled, and in the first two internal layers, and at the same time cooling the GaN transistors from the top. And that is why on all the motor drive reference design boards there is the possibility to install a heatsink on top of the GaN devices.
Thank you. Great. So talking about markets, so can you share a general perspective? Where do you see the biggest near-term opportunity for this board, but for GaN-based motor drives in general?
Sure. So the markets that we are seeing interest in terms of GaN technology are either the applications where space is a constraint. So volume is a constraint, and that means robotics, but also drones of any sizes. There are solutions to implement very innovative GaN-based inverters, both in drones and in motors, both in drones and in robotics, because in both cases there are sizes that go from low battery voltage and very few amps RMS current to higher batteries with much higher currents. So we're spanning from what an IC like EPC91202 can handle to what four EPC2361 in parallel can handle. So we're spanning from 5 and 10 amps RMS to over 200 amps RMS. So this is one. And the other one is power tools, both handheld power tools and larger power tools. They are the markets where GaN has great benefits, especially when using several discrete parts in parallel, because in such high power applications, the relative, for instance, the reduction of the DC link impacts very strongly, because often the biggest part of the cost of the inverter is due to the DC link capacitors, and in that case, being able to bring the switching frequency to a very higher value with respect to the traditional silicon MOSFET inverters, that is a key point that may change the final result of the inverter.
Very nice, very nice. Thank you, Federico. This has been a great conversation. Thanks a lot for sharing all of this information. So GaN has already transformed power conversion in areas like data center, fast chargers, and now we are seeing that this is expanding rapidly into motion systems. So my last question, looking forward, how do you see GaN in the future? GaN reshaping motor drive architectures over the next years, let's say 5 to 10?
Mm-hmm. Well, for sure, we see that some applications that we've been working and that were, let's say, a few in the market a few years ago now have become a lot. So all the applications that today have been implemented by a few, let's say, bold people who are not afraid of innovation may become the state of the art tomorrow. And let's say that as we have observed that multi-level structures, for instance, in the data centers, are a very innovative way of implementing converters using GaN. It's possible that innovative architectures like multi-level converters might be introduced also in other areas like the motor drive inverters as well.
Good. Federico, thanks a lot. Thank you for joining us.
Thank you, Maurizio.
And sharing insights into the new platform, EPC91202, and so the broader impact of GaN technology in motor drives. Thanks a lot.
Thank you, Maurizio.
And thanks to our listeners for tuning in. Stay tuned for more discussions on power electronics and GaN. Thank you.